So now what about the liquid vapor boundary? Okay. So a few things. Let's see, how much space did I give myself? Yeah, a few things on the liquid vapor boundary. No, you know what? I'm not gonna worry about that too much. I just want to get into the derivation. Okay. So we know that dP by dt equals our Clapeyron relationship, but this time it's going to be delta H of vape divided by T times delta V of vape. Okay? And now, as it turns out, the, let's see here. So, okay, yes. So as it turns out, the delta V of vaporization basically equals the molar volume of our gas, okay? So we know that technically, so I'm kind of doing this backwards, and maybe I'm having a brain fart moment here. So Vm gas minus Vm liquid, so we know that's true, okay? So the molar volume of, I'm just going to use water as an example. The molar volume of water is 0.018 liters per mole. I get that by assuming a density of 1 gram per milliliter. And if I say that there's 1,000 milliliters in 1 liter, and I know that there's 18 grams in 1 mole, and then of course you can see I'm going to have to flip all of that. But when I do that calculation, basically 1,000 divided by 18, I get 55.555 mole per liter. And if I flip that, if I do 1 divided by that answer, I get the 0.018 liter per mole. Okay, so that's where that comes from. But now what's the molar volume of a gas? nRT over P, right? nRT over P. And of course, at standard conditions, we recognize that that's 22.42 liter per mole. So compare those two numbers for just a second, right? 22.42 liter per mole versus 0.018 liter per mole. So basically, the delta H of vaporization is more or less just equal to the molar volume of a gas. Okay. So what this means now is the following. All right. So and of course, because we're going to change our pressure quite a bit, we can't just put a constant value in for the molar volume of a gas. So our equation changes. It becomes dP over dt equals delta H of vaporization divided by T. And I'm using here the molar, actually, yes, the molar volume. So it's not nRT over P, it's just RT over P. Okay. So now we're going to replace that by saying RT over P, okay? And of course, that all equals delta H of vaporization times P divided by RT squared. So I just did some algebra there. So I combine the T's, T squared. I have 1 over P, which just becomes P. And so this is now the equation that I'm going to integrate. Okay, so I've got dP over dt equals delta H times P divided by RT squared. So setting that up to integrate between P1 and P2 of now dP, so I divide over to P, okay, and now that equals delta H of vape divided by R. And we'll assume that, you know, delta H doesn't depend on temperature. It does, and of course, under certain conditions, this will lead to small error, and other conditions, this will lead to large error. And so now this is, let's see here, dt over t squared. Okay. So from here, I get a natural log relationship. I get natural log of P2 over P1 from this integral. And over here, I'll just do the integration real quick. That becomes negative delta H of vaporization over R times, and it ends up being 1 over T2 minus 1 over T1. And this is the really famous Clausius-Clapeyron equation that you most definitely used in Chem 109. Okay? And so now to do a little bit more algebra here, if I take E of both sides and multiply the P1 through, so I'm just doing 2 algebra steps and 1 here. So E of both sides, and that becomes P2 over P1, and then multiply both sides by P1. Now I get P2 equals P1, and then of course I have the exponential of this whole thing, and I'm just going to say EXP of all of that stuff, negative delta H of vaporization over R, 1 over T2 minus 1 over T1. Okay, great. And so here is my famous Clausius-Clapeyron equation. Okay? And so just a few more notes on the liquid vapor boundary. Okay? So if I just look at this, I meant to have a bigger graph right here. So if I look at this P, which technically, if I'm just looking at the vapor, this gives me the vapor pressures at any given temperature. Okay? And there's a special condition when the vapor pressure is equal to atmospheric pressure, right? We call that boiling. Okay? And so we could interpret that any point along this line is a boiling point if that is what the pressure of the liquid is, right? However, if the pressure over the liquid, so right here's my let's say beaker of water, okay? So let's say I've got P ATM, and we know that that's pushing down on the liquid. Well, the liquid pushes back on the atmosphere, right? And that pushing back on the atmosphere is the vapor pressure, right? And so when those two are equal to each other, the liquid is boiling. But what about when the vapor pressure is not equal to the atmospheric pressure? Well, that means that the temperature must be less than the boiling temperature. And thus, any one of these data points, let's say, would give us the vapor pressure of that liquid. All right? And so, of course, this also predicts, right, as you increase the pressure over a liquid, you increase the pressure required to boil it, or the temperature required to boil it, rather. Okay? And so now the solid vapor boundary, okay, turns out that it's exactly the same. So this is for sublimation. Man, that doesn't look like it says sublimation at all. For sublimation, right? Going directly to a vapor from a solid. So it ends up being exactly the same as the previous case, the liquid vapor boundary, except for now you replace delta H of vaporization with delta H of sublimation. Okay, and you have the same equation that describes that boundary. Okay, and using all three of those equations, so this equation right here, this equation right here, and this equation right here, we can reproduce a phase diagram, right? So in other words, let me find like a fictitious phase diagram somewhere in here, like a generic one. Okay, right, so on our generic diagram, right, we derived the liquid vapor equation, that's that Clausius-Clapeyron equation. The solid vapor equation is the same as Clausius-Clapeyron, except for it's delta H of sub instead of delta H of vape. And then the solid liquid boundary line, we also derived. So that gives us all three of those lines. And that's what you're going to do in your Igor 3. Okay? And so the last thing that I want to talk about,